All right, so here we begin with our next section, 3.4. We're going to be looking at some more optimization problems. So still looking at how to either maximize or minimize a function. All right, so let's look at some word problems of optimization here. Let's start off with this one here. Suppose that we have a rectangular parking lot that's going to be built along the side of a building. Suppose we have 800 feet of fencing, fence material, fencing to create this parking lot. And then suppose that for this parking lot that we're making, the side along the building needs no fencing. All right, so no fence is needed for the side pretty much that's touching the building. What are the dimensions for this parking lot for the largest possible enclosure? Okay, so let's highlight some key items here. So first things first, we're building a rectangular parking lot. And for this rectangular parking lot, we have 800 feet of material available to build it. And the key thing here as well is that the side along the building does not need any fencing. So let's picture just a little bit here. All right, so suppose here we have this big old building. Oops. Ooh, step. All right, suppose here we have this building here. All right, and suppose here we have the entrance to the building. It doesn't do just part ways. All right, so suppose here we have the side, the entrance here. And so the parking lot that we're trying to build here is going to be right in the back of this building here. So here we have the left side, the opposite side of the building, and then the right side. Okay, so here we have this parking lot that we want to build. And for this parking lot, we want to build a fence on the left side, build a fence on the right side, and build a fence here on the bottom side. But no fence is needed along the side of the building, otherwise we close off the door. Okay. Now, since these two opposite sides are on the left and the right, since they're of the same length, let's call that side, let's call it X. And for the side opposite of the building, let's call that Y. All right, so what are we trying to do here? We want to figure out the dimensions for the largest possible enclosure. In other words, we want to figure out what X and Y have to be if we want to maximize the area. Okay, enclosure means area. So for these type of problems, if you see a word where you're trying to either minimize or maximize some enclosure, that means you're trying to minimize or maximize the area of the shape that you're looking. Okay, so we want to maximize the area of this rectangular parking lot. Okay, so the next thing we're going to think about then is the equation of what we're trying to maximize. Okay, so let me write this down here again. So again, we want to maximize the area. Let's say WWT for we want to. I believe I used that before. If not, this means we want to. All right, so we want to maximize the area of this rectangular parking lot. Okay, so first let's create an equation relating our two variables of interest here, since we're trying to find the dimensions of X and Y with respect to what we're trying to maximize. Well, what do we have? We have a rectangular shape here, right? A rectangular parking lot. How do we maximize the area? Or let me rephrase that. how do we calculate the area of a rectangular shape? What we call from algebra, the area of a rectangle is just the length times the width. So here we have our first equation of interest, which is the area that we're trying to maximize, a function that we're trying to maximize, which is going to be in terms of x and y. In this case, length times width, right? Yeah, algebra review. Length times width. I'll use dot for times. Or in our case specifically, x times y. Okay, so this is the function that we want to maximize. And let me call this A for area. All right, so we want to maximize this function A. That's in terms of x and y. And recall from the previous section from 3.3, what does it mean to either maximize or minimize a function? It means that we need to find its critical numbers by utilizing the first derivative. But what's the problem right now? What's the issue that we have? The issue that we have here that's not going to allow us to find a derivative just yet is that this function of the area contains two unknown variables, x and y. What we have done so far throughout these set of chapters is finding the derivative of a function in terms of just one single variable. But here we have two unknown variables. So for these simple problems, what we want to try to do here is we want to try to figure out how can we rewrite the equation that we're trying to optimize. How can we rewrite it in terms of just one single variable? And to do that, we have to use some other given information that's relating our two variables of interest. Let's go back here. Look what else it's telling us. Recall that to create this fence, we have 100 feet of material available, right? Meaning to surround this fence. Let's see, how can I draw this? I'll do this. If to surround this fence here, we have 800 feet available to create the fencing around this parking lot. 800 feet to surround this rectangle. What do we call this distance that is surrounding the outside, the line segment of a rectangle? In other words, we have 800 feet of perimeter to cover around this rectangle. So 800 feet, that's representing our perimeter. Okay, so our perimeter, the fencing material that we have to surround this fence is going to equal 800 feet. I'm going to assume we want to use all the material that we have. Okay, so our perimeter is 800 feet, but how do we define the perimeter of this specific rectangle that we're working with? Again, what does the perimeter of a polygon represent? The perimeter of a polygon represents the distance along the sides of that shape. Meaning the distance around the left side plus the distance along the bottom side plus the distance along the right side. Or in our case, our perimeter is going to be twice x plus y. Because these two sides on the left and the right are the same length, but the bottom will not be. Or it could be, we don't know yet. So our perimeter is going to be 2 times x plus y. So these three sides should equal 800 feet in total distance. Okay. Let me delete that feet. I don't need that feet right now. So why did we formulate this? Because what we can do here is we're going to use this given equation, this given information to help us solve for this new information, for this unknown information. Because what we're going to do is take this given equation and use this to rewrite the equation that we're trying to optimize in terms of just one single variable. In other words, we're going to use this given equation to substitute into our new equation. So let's see, what can we do here? Let's solve for y using the given equation. So let's solve for y. To give us y is going to equal 800 minus 2 times x. All right, I just subtracted 2x from both sides. So minus 2x to give us 800 minus 2x. Okay, so what we can do now is we can use this equation that we rewrote and substitute it into our function that we're trying to optimize. So we're going to plug this in, 800 minus 2x, into y for this area equation. All right, so now we're going to have, so we're going to take this, let me write this somewhere. It's going to take what we found here and substitute into y there to give us a equals x times parentheses 800 minus 2x. Distributing that x on the outside gives us our area function to be equal to 800x minus 2x squared. So now our function that we're trying to optimize is in terms of just one variable, which is that variable of x. Let me just double check, make sure. Okay, so here we rewrote our equation in terms of just one single variable. All right, so using some methods of substitution here. All right, solving a system of equations. Okay, so now that we have written this equation that we're trying to optimize in terms of just one variable, what will be the next step? The next step is not to set this equal to 0. Do not set this equal to 0 just yet. What are we trying to do? We're trying to optimize, we're trying to maximize the area. Again, from 3.3, to maximize a function, we have to find its derivative and solve for the critical numbers. So the next step is to find the derivative of this function with respect to x. So let's find a prime here. All right, so the derivative of 100x respect to x is just 800 minus the derivative of 2x squared gives us 4x. Okay, we have to find the derivative of the function trying to optimize, and then we set equal to 0 to find its critical numbers. So 0 equals 800 minus 4x, using some algebra here, solving for x, gives us 200. 200 feet to be more specific, right? Subtract 800 to the other side, negative 800 divided by negative 4 gives us 200 feet. So the sides on the left side and the right side each should be 200 feet a piece. Okay, so that's one side of the dimension. Oh, that's one dimension, I mean. But we're not finished just yet because we also got to figure out how long the bottom side needs to be. And how do we figure that out? Well, just take what we just found and plug it into our substitution equation that's already solved for y. Okay, so now let's take y equals 800 minus 2 times what we just solved for x, which was 200. To give us the y should be 400 feet. Okay, so according to what we found, if we want to find the optimal maximum size of this, I don't know if he's doing that. Let's do this. If we want to find the optimal maximum size of the parking lot, then the sides on the left and the right should be 200 feet each. And then the bottom side here should be 400 feet. And if we want to find what that maximum area is going to be, then all we need to do is just multiply these two against one another, right? Our length times our width. All right, so let me write this here. All right, so our maximum area, I'll say max for maximum area is going to be A equals X times Y. So in our case, 200 times 400 to give us a maximum area here of, what would that be? 2 times 4, 8, 4 zeros of 80,000 feet. 80,000 feet square is our maximum area if we make the sides on the left and right 200 feet each, and the side on the bottom 400 feet. Okay, let me summarize this here. All right, so the largest possible enclosure is when the length is 200 feet and the width is 400 feet with a maximum area of 80,000 feet square. Okay. And this is how these problems usually go for these optimization problems in 3.4. Okay, we're trying to optimize a certain function, so we've got to formulate the equation of that function relating our variables of interest, usually 2 of them. Then we got to use some prior information, some get information that's already relating our 2 variables of interest, and use that information, formulate another equation, and then use that equation to substitute into the one that we're trying to optimize. So we write it, that function that we're trying to optimize in terms of one variable, find the derivative, set equal to 0, solve for that unknown variable to get our critical value, and then plug it back into, it could be into the given equation to solve for the other unknown variable. Okay. And if we want to find our maximum or minimum value, plug in the values of our 2 variables into the function that we optimized. All right.